In our previous lecture yesterday, we have discussed design of control systems and design of pole placement. In that, we have tried to find out using the control signal u is equal to minus k into x of k, where k is the feedback system's feedback gain matrix, and when there is feedback here k, it means that we are going to see some error and trying to make that error to be equal to 0, right? And so with this formula, the formula that we have derived using the design using pole placement or pole assignment technique, that is, we can place our location of poles anywhere in the desired locations, and k is the formula that we got yesterday, where that is alpha n minus an, alpha n minus 1 minus an minus 1, so on, alpha 1 minus a1 into t inverse, where t is equal to mw and m is the controllability matrix. We have assumed that the system that we have considered here in this case is a linear timing variant system, which is g x of k plus h u of k, right? This is completely state controllable. We have assumed that this system is a completely state controllable system, right? So M is our controllability matrix here, and W is the system which we are obtaining from the coefficients of the characteristic equation of this form, that is Zi minus G. The determinant, if we consider, we have considered it as plus a1 z power n minus 1 plus so on plus an minus 1 z plus an, and this can be equal to 0, and the eigenvalues of this are found out, and the desired eigenvalues are found from this equation, and the desired eigenvalues, we have chosen them to be some other variables. You can say mu1, mu2, mu_n, or in fact we have considered here w here. From that equation you have this as an minus 1, an minus 2, a1 1, an minus 2, an minus 3, so on, 1 0, so on, a1 1 0 0, and 1 0 0 0. So this W matrix is obtained from this characteristic equation, the coefficients a1, an minus 1, an, right? And M is the controllability matrix of that system. What is the controllability matrix? We have H, GH, G square H, G power n minus 1 H. The rank of this matrix is assumed to be equal to n, which is the order of the system. So this is what we have discussed yesterday. The necessary and sufficient conditions, we have proved that the system must be completely state controllable to find out the feedback gain matrix K, right? If the system is completely state controllable, then it is possible for us to design a feedback gain matrix K in this way. And see this one, an, all a's, a1 a2 an are all coefficients of this matrix, and by substituting u is equal to minus kx in this equation, what is the equation I will get? X of k plus 1 is equal to g x of k minus h u of k is k x of k, h x k x of k, or g minus hk into x of k is what we will be getting. Now this is again another matrix, and zi and the characteristic equation of this equation is modulus of Gi minus G plus Hk. If we consider this equation, then we can write this equation as, these are desired allocations, desired pole locations. This matrix is obtained from desired pole locations. Therefore, Gi minus G plus Hk, G power n plus alpha 1, G power n minus 1, alpha 2, G power n minus 2 plus so on, plus alpha n minus 1 Z plus alpha n is equal. So, these alphas we are getting here in this matrix, alphas, and A's we are getting from the original system characteristic equation, and alphas we are getting from the desired system characteristic equation. Therefore, these values can be obtained, T can be obtained, T is MW, right, and we can obtain all these values without any problem. So this is what we have discussed yesterday regarding design of pole placement in design of control systems. Now this is not the only solution for finding out the feedback gain matrix K. We have many other forms, and in that we have this, we have one of this form which is called the Ackerman's formula, which we will be discussing today for the same system which we have studied yesterday, right? And we are assuming that the system is completely state controllable, and we will stick to that basics of assuming all the system to be completely state controllable. Now let us discuss the same system. X of k plus 1 is equal to Gx of k plus h u of Gx of k plus h u of k. Right. Now the original system characteristic equation is z power n plus a1 z power n minus 1 a2 z power n minus 2 plus an minus 1 z plus an equal to 0. And now when you are applying minus kx of k, what is the equation that you are going to get? X of k plus 1 is g minus hk into x of k, right? So the desired system characteristic equation, we have z power n plus alpha 1 z power n minus 1 alpha 2 z power n minus 2 plus alpha n minus 1 z plus alpha n is equal to 0. Now these are the things which we are having it here. Now the Cayley-Hamilton theorem, which states that Cayley-Hamilton theorem based on Cayley-Hamilton theorem, what I wanted to discuss now is, let me consider G minus Hk as G cap. G bar is G minus Hk. Now this is what we will assume. G bar is equal to G minus Hk. So instead of this, the Cayley-Hamilton theorem will state that it will satisfy its own characteristic equation. Now this is the characteristic equation for this system. Therefore, this is G cap, G bar for us, and that G bar can be replaced here, right? So G bar power n. Instead of Z, we replace G bar power n plus alpha 1 G bar power n minus 1 plus alpha 2 G bar power n minus 2 plus so on plus alpha n minus 1 G bar plus alpha n. Since G is a matrix, alpha n is a coefficient or value, then I will replace it with, I multiply it with identity matrix I. So G, now we have this according to Cayley-Hamilton theorem, G bar satisfies its own characteristic equation, therefore we have written this equation. Now based on this equation, we will try to find out the Ackerman's formula that is required. Now we know that G bar is G minus Hk. Now let me say what are the things that we require here. G bar is required, G bar square is required. Now G bar is G minus Hk. Now G bar square, what is it? G minus Hk whole square. If we multiply these, what do we get? G square minus 2GHK, this is A minus B whole square, plus H square K square. So what do if I simplify this, now I'll make this as minus GHK minus GHK, that is minus 2GHK. So 1 GHK I'll replace it here, right, that I have brought it here, and minus GHK plus H square K square, this is here, right. So I can just consider here as minus of G minus HK into HK, or we can have this as HK is common and G minus HK, right, and G minus HK is nothing but G cap, G minus HK is nothing but G cap, therefore we have this. So G cap square is G square minus GHK minus HK G cap. Similarly, G cap cube, if we multiply this, we get this term of this kind of equation, which is nothing but G cube minus G square HK minus G HK G cap minus HK G cap square. This is what we will be getting when we are going for G cap cube, right. So similarly, G cap power n gives me G minus HK power n. We can multiply all these things and verify and find out what is what in this. So this is a generalized equation. This is a generalized equation power n, G power n minus G power n minus 1 HK minus G power n minus 2 HK G bar minus so on G power n minus 3 HK G bar square. When G is reducing its order, G bar is increasing its order. So minus dot 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 minus G H K G bar power, when you have 2 here it is 3, therefore n minus 2 and minus HK G power n minus G bar power n minus 1. Now this is our characteristic equation, right. So if you substitute it here, you can have that value, right, all the different values. So Cayley-Hamilton theorem, we will be substituting it here. Now what we require to do is, we require to substitute these in this equation. When we substitute this in this equation to find the Ackermann's formula, alpha ni. Now I start with this vector, alpha ni plus, for simplicity I am trying to write it in this form, alpha n minus 1 G bar is G minus HK plus alpha n minus 2 G minus HK square, G minus HK whole square. So this is G square minus GHK minus HK G bar. Okay, so I will erase it up to this point since we have finished this part, plus alpha G cube minus G square HK minus G HK G cap minus HK G bar square, right, plus so on 1, or you can say simply, in order to reduce the complexity, I will just substitute g bar power n. G bar power n 1 into, isn't it? Or I into, you can say that I into or 1 into, or simply write this matrix equation. Therefore, what is g power power n? We have g power n minus g power n minus 1 hk, g power n minus 2 hk g bar minus g power n minus 3 hk g bar square minus g hk g bar n minus 2 minus hk g bar power n minus 1. So this is what we have obtained in this Cayley-Hamilton using this. Now this is our characteristic equation which we got. Okay, which is equal to 0. Sum of all is equal to 0. Now just consider this equation. Alpha ni, alpha n minus 1g, only the first terms can be considered. Just consider the first terms. You can say that alpha ni plus alpha n minus 1g, plus alpha n minus 2g square plus alpha n minus 3 g cube plus so on plus g power n. These are the first terms which I have considered. Plus, now I will take the last terms where we have hk common. Hk. Right, hk. So, minus h. So, minus h is what I am considering it here. Minus h. K is a feedback matrix. Therefore, alpha n minus 1 k minus alpha n minus 2 kg bar minus alpha n minus 3 kg bar square minus is already considered, therefore I will put all this positive. Minus is already considered here, so minus is nullified. So on, the last term is plus k g power n minus 1. This is minus h. Now consider GH terms. Wherever we have GH terms, coming from the last, you will be having GH terms. Minus GH minus GH. GH is alpha n minus 2k plus alpha n minus 2k, alpha n minus 3gh, alpha n minus 3 kg bar, right, then so on, plus so on, kg bar n minus 2, kg bar n minus 2.